I guess we'll wait another minute or so just to see if people show up in the waiting room here.
Also, if you hear any commotion during the talk, I will just put the disclaimer that I have a 5-month-old puppy and she is a troublemaker. So like, just be forewarned that there may be small bouts of commotion at certain points.
I was wondering if Mania would make an appearance today.
I will, if the talk goes well, at the end of the talk, I will have a little cameo from Meme.
All right, I believe I've successfully used the waiting room to let everyone in. So I'm happy to now actually officially introduce Marissa Loving. So she's an NSF postdoc at the Georgia Institute of Technology. She earned her PhD from UIUC, so the University of Illinois at Urbana-Champaign. Advisor was Chris Leiniger. And I think her work is really centers around low-dimensional topology and really the mapping class group. And I think studying really beautiful objects like these graphs built from curves on surfaces and studying the pattern of how those things intersect. I mean, really fantastic work. And also, I should maybe also mention that I really enjoy her presence on Math Twitter. So I'd encourage you to check her out there as well. Okay, but now it's our time now to hear from Marissa Loving. She'll be telling us about automorphisms of the Kcurve graph and building mathematical collaborations.
Awesome. Thank you so much for that introduction, Jim, and thank you to all the organizers for putting this together and for inviting me, and for all of you for being here so early on a Saturday morning. I know for many people it's even earlier than it is for me. Yeah, so today I'm going to tell you a bit about automorphisms of the Kcurve graph. And I'm also going to tell you a bit about building mathematical collaborations, because for me, this was something that always felt very mysterious. And to be honest, it still feels very mysterious to me. But I spent some time thinking about the way some of my collaborations have come to be. And I thought it would be good to sort of talk about that, how they came together, sort of what were important pieces in making them work, and maybe share that with all of you, as I know many of you are sort of early on in your math journey. And so mathematical collaborations are going to become larger and larger parts of your work. Okay, so just a little bit of an outline of the talk. I'll start off by just talking a little bit, first an intro, a little bit about myself, and then a little bit about what I think of when I think about a math collaboration. So that's going to be the first chunk of the talk. Then I'm going to talk a bit about this program called Summer ICERM. Some of you may already know of this. Maybe there's some folks who participated in it here. So this is a summer undergraduate research program. And I'll talk about when I participated as a graduate student mentor in 2018. And in this chunk, I'll also then give a mini math research talk. So this is when I'll actually talk about these automorphisms of the Kcurve graph. And then I'll talk a little bit about sort of what the next steps were after that summer program. And then I'll end with sort of a chunk that's just talking a bit about some practical tips for mathematical collaborations in general. Okay, so to say a little bit about me, I have this math timeline. Okay, so this is of course very abbreviated. My math timeline, I guess for most of us, our math timelines probably start when we're kids. But I'm going to start it with sort of when I started with academic math. So I'll start in 2009, which is when I started my undergraduate at the University of Hawaii at Hilo. So I had a 4-year chunk there. I'm from the Big Island. I'm Hawaiian. I grew up on the Big Island, just outside of Hilo, in a little town called Honolulu. And so I lived at home with my family for undergrad. I studied math and computer science. So I graduated with a BA in math and a BS in computer science. And the fall of 2013 is when I started my PhD in math at the University of Illinois at Urbana-Champaign. Okay, and then I'm going to skip ahead. Of course, many things happened in this 5-year gap between 2013 and 2018. This is sort of when the bulk of my graduate school career was happening. But sort of in the middle of that time, I was able to be the grad student mentor at ICERM. which was sort of an important sort of milestone for me. And then in 2019, I graduated with my PhD from UIUC, and I saw an NSF postdoc here at Georgia Tech. Okay. And then another important date that I've added is this year, actually, this summer, where I was actually able to be the faculty mentor together with Sudhi Krishna of an RU group for the first time. And one of my RU students, Dane Galero, is here and gave a talk yesterday. Okay, and then of course today I'm here. Okay, so this is my extremely abbreviated math timeline. And so now I want to go over the same timeline, but from the perspective of my mathematical collaborations. Okay, sort of talking about where I started, where I am now. Okay, so let's go back this exact same timeline, and now let's fill it in from this viewpoint. Okay, so what were my sort of mathematical collaborations at each of these stages? Okay, so when I started undergrad, I had never done math collaboratively. I was homeschooled growing up, actually, until I started undergrad. And so really most of my math education before I got to college was very solitary. It was like reading textbooks, doing exercises, taking exams and things like that. But it was sort of a one-on-one thing, me and my book, not really a collaborative experience at all. And then there was undergrad. So during undergrad, I really enjoyed doing math with my classmates. I was sort of super lucky to have like a really close cohort of about, I guess there was like maybe 8 to 10 of us who were taking a bunch of our math classes together, and we would have study sessions together. We had like a study group that studied for the Putnam exam together. We had parties together. We just did a lot of stuff together. And so there was lots of sort of math happening, but not so much math research. We were really sort of working to learn new math in our classes or in reading groups and things like this. And then I added a sort of extra marker on this timeline for this space in between 2013 and 2018, because that's sort of when I was in the thick of my grad school time. And this was a time when I really did not have good mathematical collaborations or experiences, even talking math with people. I had sort of at the beginning of grad school, I had some not so great encounters with some of my classmates that really made me feel like I didn't bring anything to the table when we were talking math. I didn't bring enough expertise or anything like this. And so I really sort of shut down a lot. I avoided talking math with other people as much as possible, which is really not the optimal way to go through grad school. It's not really the optimal way to learn or do math, but that's sort of where I was at. And so this is why the ICERM program was so important to me, even though you might think like, well, you're a grad student, like isn't the ICERM program mostly focused for undergrads? What was so important about it? Well, it was really a point for me that started to allow me to move towards talking math and doing math with other people again, because it was such a like warm and collaborative environment. We really spent a lot of time talking to each other about math. We were very supportive of each other's sort of learning math, sort of engaging with new math. A lot of us were sort of engaging with math that we hadn't seen before. So we sort of were coming in on equal terms. And I really felt it was just exciting. It felt invigorating and it felt really good. Okay, so this was sort of an important time of transition for me mathematically. And then by the time we get to 2019, I was starting to build some independent collaborations. And so here when I say independent collaborations, I mean collaborations that weren't sort of focused on me talking about math with my PhD advisor. These were sort of things that I was starting to be able to talk about math with like my peers. So maybe some other grad students or maybe like a postdoc. And so that was sort of really important. I was starting to be able to do that by the end of my grad school experience. And if we fast forward now to today, I have many active and ongoing research collaborations. And we'll talk a little bit about how some of these collaborations really got started a bit later. And then of course, you know where I am today. Okay, I'm right here. Okay, so that's just a little bit of an intro to me. So now let's actually talk about sort of what the definition of the thing that we're talking about in this talk is, right? Which is what is a mathematical collaboration? Okay, so of course, there's lots of different things that people could mean when they talk about mathematical collaborations. I'm sure each of you sort of have something that comes to mind when you think of that yourself. But I want to give sort of a specific type of answer. Okay, so my idea, what I'm going to sort of be meaning throughout this talk when I talk about a math collaboration, is it's going to be a group of people doing mathematics together over an extended period of time. Okay, so this sort of I think both of these parts are really important. Of course, the doing math is important since it's a mathematical collaboration and not just a collaboration. But I think sort of this aspect of sort of coming back to this relationship over some extended period of time is also sort of an important aspect of a collaboration. Okay, so what are some, whenever we introduce a concept, right, we should give examples. So I've already, I think, sort of in passing mentioned some of these examples. And folks should feel free to put other examples that come to mind in the chat. But some of the examples that sort of come to mind right away are things like a study group, right, for a math class. This is a group of people who you're doing math with over an extended period of time. Okay. You could have an RU group, right? Maybe this is a group of your peers that you're doing math with, or maybe this is a sort of research advisor that you're doing math with over a summer. That definitely counts as a collaboration. It could be a sort of reading group. Maybe you and some of your friends get together and decide you want to read a textbook, and you take turns presenting the material to each other, talking through the exercises and things like this. These are all examples to me of mathematical collaborations. Okay. So these are some examples. What are some other things that I sort of like to keep in mind when I talk about it? Do you hear? This is Mei. She's trying to get my attention. Mei, you have to go now, honey. So what are other things to keep in mind, right, when you have a mathematical collaboration? I think it's important to note that for me, a mathematical collaboration is independent of output. So sometimes I think, especially in math, we can be very focused on sort of what are we doing and like what do we need to get out of this, right? We need to have I need to have a paper. Like I'm applying for grad school, I need a paper. Or like I'm applying for job soon, I need a paper. Or and we think of like what we want to come out of it at the end. But I think for mathematical collaboration, it's independent. If you're spending time thinking about math and doing math with someone for a long time, that's a collaboration regardless of what happens at the end, right? Okay. It can, as we sort of mentioned in these examples, it can be led by sort of a senior member, an advisor, or it could be co-facilitated by you and your peers. And finally, it can be either really amazing experience. It can be sort of a time to sort of bring a lot of sort of synergistic perspectives to your work. Or depending on sort of the way that that is structured, it can be a really unhappy and discouraging experience. Okay, so this is also something to keep in mind. Okay, so back to our outline. So I think I've covered my sort of first step. Okay, I've given a little bit of an intro. And so now I want to turn to this Summer ICERM. Okay, so let's talk a little bit about this. Okay, so again, for those of you who haven't done this type of program, so this is an RU, but it's sort of a RU that's a little bit bigger than sort of some of the RUs that are like one person, one faculty member in a group. Typically, there's like 3 to 4 faculty mentors and like 4 or so graduate student mentors, and then maybe 20-ish undergraduate researchers. Okay, so that was sort of the structure that we had the summer that I did in 2018. And I was the graduate student mentor on 2 projects. So the first project was automorphisms of the Kcurve graph. And the second project was this project, length and self-intersection numbers of geodesics and hyperbolic surfaces. And I'm really going to focus on this one, okay? Because this is the one that has sort of led to some ongoing work after the summer ended. But I will touch back on this one a little bit later in the talk. Okay, so who was this project? Okay, so this project was led by Tarek Algad. He was one of the faculty mentors for the Summer ICERM in 2018. He was a postdoc at Brown at the time, but he's now a tenure track faculty member at Haverford College. And then the graduate student mentors were myself and Sunny Zhao, who graduated with her PhD in math from Brown last spring. And then we had 3 undergraduate researchers, Yassine Chandran, Rob Oakley, and Roberta Shapiro. Okay, so they're all actually now 3rd-year graduate students. So Yassine is at the CUNY Grad Center, Rob is at Temple, and Roberta is here at Georgia Tech as well. Okay, so this is sort of the group of people that we had. And now I want to give us a little mini math research talk. Okay, so we're going to change gears a little bit from talking about math collaborations. We're going to talk a little bit about this project, and then I'll talk sort of about sort of how we sort of wrap this project during the summer and then what work went into it after the end of the summer. Okay, so automorphisms of the Kcurve graph. Okay, so what was our main object of study here? Our main object of study is surfaces. Okay, so I've drawn a couple of examples here. I've drawn sort of one that may be pretty familiar to many people. It's a sphere. Okay, so you could think of just sort of a solid ball, but then you don't want the filled in ball, you just want the skin of it. So if you like take an orange, you take the skin of that orange. Okay, so these are sort of all two-dimensional objects, not three-dimensional objects. I have this sort of one donut hole looking thing, okay, which I'll call the torus. And I'll describe this sort of hole here as being its singular genus, okay? And then I have these sort of higher genus surfaces. So here's my genus 2 surface, right? And my genus 3 surface. Right, and again here, I'm sort of counting these holes here as my genus. Okay. So I've drawn this list, but you could sort of keep going, right? You could easily just add sort of another hole here, right? You could turn this into a genus 4 surface and so on. You could sort of keep going. And it turns out that if you're looking at surfaces that don't sort of have a point removed, right? You don't sort of take out a point like that, like a pinprick, or you don't sort of cut out like a disc like this, then if you just look at closed surfaces, then in fact, these are sort of all of them. Okay, so this is called the classification of surfaces. And it tells us that our closed surfaces are really determined by their genus. Okay, so here I said sort of up to homeomorphism. I'm not going to get into too deep what that means, but we can think of this as just if you can sort of take one surface and make it look like the other without sort of cutting or tearing it anywhere, just sort of smoothly squishing it from one to the other. Okay, so for example, we could make this look sort of like a torus if we could cut it, right? If you could sort of punch all the way through with a cookie cutter, and sort of take a piece out in the middle and sort of squeeze it together, you could make it look like a torus, but that wouldn't be a smooth or a continuous type of thing to do, right? We'd have to be sort of really destroying our surface to make that happen. Okay. So one thing that is sort of fun with this is that this allows us to, for example, to distinguish between these two surfaces, or in fact, to be able to say that they're the same, right? We can sort of count the genus, right? So we have one genus here, we have one genus here, we have one genus here, and here we also have 3 genus. Okay, so the classification of surfaces tells us, well, these should be the same. Okay, so a fun exercise, and I'll leave that for any of you if you are sort of losing your sort of train of thought during my talk, feel free to spend some time thinking about how you can show that these two are the same through some sort of nice sequence of continuous moves. So really what I mean is sort of draw some intermediary pictures that allow you to sort of move from one to the other. Okay, so that's sort of a neat little application of the classification of surfaces. So this is one of our main objects of study is surfaces. The other object of study is curves. Okay, so I'll draw a few examples of what I mean by a curve. When I'm talking about a curve, I really mean sort of like if you start at a point and you sort of draw a nice line embedded in your surface, and then you come back to where you started. So you close your loop back up. Okay, so you can sort of think of it as putting a circle into your surface in some interesting way. So for example, you could draw this curve. This is some nice curve. You could draw a curve like this, that's sort of going around the other direction of your torus. Both of these curves are examples of something called a simple curve, because they don't cross themselves, right? That's different than if I, for example, draw this curve, right? This curve here has this sort of intersection here, and there's no way of sort of pulling that intersection off, right? That's sort of a crossing, an essential crossing in your curve. So this is a non-simple curve. Okay. I also, I'm going to focus in most of the talk on these sort of simple curves. I also want to sort of have curves that are actually interesting on my surface. So for example, I wouldn't want to consider a curve like this. So here's a curve I could take, right? Here's this curve which sort of cuts off the top of my sphere. So if I draw on the side, you can see a little bit better what it looks like, right? It's just a curve like this. And so it's bounding some sort of nice little disc like this. This sort of curve is not the type of curve that I want to look at because I can just sort of squish this in, right? I could sort of squish, 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 and I could push it all the way down to just a little point, right? That's different than, say, this curve here, where there's no way to pinch it all the way down to a point without breaking my surface, right? Without sort of tearing my surface. Okay, so these are two sort of simple curves. I can also talk about sort of when two curves are the same, right? For example, if I draw this blue curve here, and then I draw this like orangey curve here, I've sort of drawn them separately, but it's easy to see that we could just sort of slide them together, right? You could just sort of slide them along this pink path, and they look the same. So if whenever I can sort of do that, I can just sort of smoothly slide two things. I'll think of them as being the same, and I'll say that they're in the same homotopy class. Okay. And so just one picture, because I know it's easy to think based on the pictures I've drawn here, that when I talk about a simple curve, I'm really just sort of talking about something very basic looking like this. But just to convince you that simple curves can be very interesting, I drew beforehand, because I knew I wouldn't be able to draw it on the fly, a more complicated simple curve, right? So this curve is still simple. It doesn't have any self-intersections. But as you can see, it sort of has a lot of interesting things going on. And it's also sort of traveling all over my surface and sort of seeing a lot of the topology. Okay, so I just wanted to sort of put that as a warning sign that although they're called simple, and in many ways they are simple, you can have sort of a lot of interesting things happen when you study simple curves. Okay, so here are my sort of two main objects of study, my surfaces and my curves. And one of the ways that I study these surfaces and curves is by studying an associated group. Okay, so I'm only going to sort of define this group very vaguely, but it's going to give us the right flavor to think about for the rest of the talk. Okay, so I'm going to define this group called the mapping class group. And I'm going to say that the mapping class group is the collection of symmetries of a surface. Okay, so let me introduce a little bit of notation for this. Okay, so this is my definition that I'll use. And this is the notation. So I'll say for a surface S, this mapping class group of S is denoted by mod S. Okay. So if you ever see this mod S floating around in something you're reading, you'll know that it's sort of describing this group of symmetries of a surface. So what do I mean when I say symmetries? Some of you may have thought before of symmetries of sort of rigid objects, like a square, for example. You could think of symmetries of a square in terms of sort of what are nice or rigid rotations that we can do of that square that sort of preserve the properties of a square. So what are the properties of a square? Well, all my angles are 90-degree angles, and all my sides have the same length. So what are things that we can do to this square that preserve those properties? Well, we can rotate, right? If I rotate by 90 degrees or pi over 2, all of my sort of edges go to all of my other edges, all of my angles are preserved. Or I could do something like take my square and I could reflect it around a line. Well, maybe that's not right in the middle, right? We could sort of reflect it across this, right? This is another thing that preserves sort of all the properties of my square. And so I can think of these as symmetries of a square. But how do you take something that's like a symmetry of a rigid object like this and think of what a symmetry of something so floppy and soft as a surface could be? Well, you can use similar types of things. So I won't give all the types of examples of symmetries we can have of a surface, but I'll draw a few examples to give you some idea. Okay, so I'll start by showing a symmetry of this genus 3 surface, which I've drawn here sort of differently than I drew it last time. I drew it as symmetrically as I could. It kind of looks like a fidget spinner. So here I'm drawing this dot to think about sort of an axis through the middle that I can think of rotating my genus 3 surface through. And then I can think of rotating my surface, right, by 2 pi over 3. Okay, so I'm taking each of my handles and I'm just clicking them one to the next, just like if you had a fidget spinner, right? And you're just sort of spinning it. And you can see that this thing is acting on curves on my surface. So this purple curve will get moved over to this pink curve, will get moved over to this yellow curve, right? And then the yellow curve will get moved back to the purple curve as I sort of move it around. Okay, and of course you can look at what happens to other curves on your surface as well. So this is sort of an interesting way to sort of see the action on your surface when you're performing these symmetries. Another symmetry that we could do would be to take this genus 2 surface and sort of skewer it right down the middle, like if you're getting ready to roast a hot dog. And then we can think of just rotating it around that axis so that the back is on the front and the front is on the back. So this is something that's called a hyperelliptic involution. I won't say that word again. It's not important. If you ever want to look up some interesting and pathological homeomorphisms of surfaces, feel free to. Okay, so that's another type of symmetry in my surface. And again, we can sort of see what happens to curves. This curve here, right, is going to get flipped up to this curve here. And then finally, I've drawn sort of another type of like rotation, but of a little different flavor. Instead of taking my rotation and sort of trying to act on my surface as I've drawn it here on the left, I'm instead going to give a different representation of my surface. So it turns out that given a surface of genus G, you can always chop it up into some polygon. Okay, so for my genus 2 surface, I can chop it up into this 10-sided polygon. Okay, and so instead of acting on my surface directly, I can act on this polygon, and that's going to give me a map of my surface. Okay, so now my rotation is a little bit more subtle, right? I'm doing it over here on this surface, this sort of polygonal representation of my surface. And I'm rotating sort of so each side is going to the next one. And you can see that this is sort of something interesting is happening here, because if you take a curve like this, right? So this represents as some simple closed curve on my surface because this side is getting glued to this side, right? So that line that I've drawn actually glues up to a simple closed curve. That's going to get spun over to this curve here. Okay, so all my curves are sort of getting moved off myself as I sort of twist around. Okay, so these are a few examples of symmetries. There's lots and lots of other symmetries of surfaces. So the mapping class group is it's an infinite group. It is finitely generated, which is nice, but like there's lots and lots and lots of different symmetries that we could have. But I want to talk now about sort of taking all of this sort of topological data we've been looking at, right? We've been looking at surfaces, we've been looking at curves on our surfaces, and turning it into something that's a little bit more combinatorial. Okay, so this is where this notion of the curve graph, which Jim mentioned at the beginning, comes in, right? So the curve graph is giving us a way of transforming topological data into combinatorial data. So this is sort of the mantra that I sort of think of when I think of the curve graph. And so the curve graph is defined in the following way. So a graph, right, is just a collection of vertices and a collection of edges, right? So your edges are coming between your vertices. And so all I need to tell you to define this graph is sort of how do I define my vertices and how do I define my edges? Okay, so my vertices are going to be these homotopy classes. Of simple closed curves. So again, homotopy class here, I'm just saying that because if I have two curves, I can sort of just slide into each other. I want to count those as the same. I don't want to just sort of push off a curve to get another copy of it and think of that as being sort of distinct. Okay. And then my edges, I want an edge between any pair of curves which can be realized disjointly. So here, this is why it's important that the homotopy is in the previous thing, right? Because a curve, you could sort of always push off a copy of itself and they look disjoint, but those are really the same curve. Okay, so those don't really count. So let's draw a picture that will help us sort of process this definition. Okay, so I'm going to draw, let's draw this curve. Okay, so I'll draw a curve and then I'll draw its associated vertex, right? Here's a simple closed curve, so it has some vertex. Here's a simple closed curve, right? So it has some vertex. And I'm just going to keep filling these curves And then we can put together where the edges should be between these curves in my curve graph. So here's another simple closed curve. And finally, I'll put in this simple closed curve. Okay. And so now I'm going to say, well, which of these curves are disjoint from each other? Okay, and again, it's important that I mean like sort of that they can be realized disjointly. So for example, this curve, I could have drawn it like this, but this can just sort of get pushed this way, right? This can get pushed this way, and then we sort of don't see those intersections anymore. So whenever I say disjoint, I really mean that it has sort of a disjoint representative. So let's just put it in the disjoint representative. Okay, so well, first of all, we just saw that my pink and blue curve, they don't intersect each other. So we have an edge here, right? Here's my edge. My red and blue curve don't intersect each other. They're sort of on opposite halves of the surface even. So we can put in a curve there. My pink and green curve, they intersect, and they intersect twice, right? And there's no matter sort of how we rearrange, there's no way to sort of pull that pink curve off my green curves because they're sort of hooked around those two genus on either side, right? So this is sort of essential intersections we're seeing. But I definitely do not see any intersection between my red and green. And I also don't see any intersection between my green and blue. Okay. And then again, here, I don't see an edge between red and pink because I have this intersection and there's no way to sort of pull these curves off of each other. They're sort of both intrinsically looped around that sort of genus to the right. Okay, so this is just a very toy picture of what a piece of the curve graph could look like. But I will point out that the curve graph is actually like an infinite valence graph. And so this is like an extremely simple look at what sort of a piece of the curve graph could look like. And in reality, it's sort of a very complicated and hard to understand graph. I think I saw someone's hand go up, but then it went down. But feel free.
Yeah, I was wondering if the people study like the multiplicity. So you said the green curve and the pink curve intersect twice. So could you like make a graph where you like assign multiplicities to each edge based on like how many times they have to intersect? Is that something?
That's a great question. I don't know of anyone who has done anything like this, but we are actually going to look at sort of a similar flavor of sort of generalization of the curve graph in just a little bit.
Okay. Great, thank you.
So one of the things that is really handy about the curve graph and which justifies this sort of idea here that we're really turning this topological data into combinatorial data is this theorem of Evenoff. Okay, so this theorem of Evenoff tells us that in a very real way, the curve graph is somehow capturing the interesting information about my surface. Okay, so it says that the group of symmetries of the curve graph is in fact the same as the group of symmetries of a surface. Okay. And there's a little bit of ambiguity that I'm sweeping under the rug here. Typically, when people talk about the mapping class group, we talk about sort of mapping class groups of symmetries which are sort of preserving the orientation of my surface. And when we're talking about this group of symmetries and sort of throughout this talk, I'm talking about something called the extended mapping class group. So we actually sort of allow for these orientation reversing things. But that's okay. I'll just like, that's just in the background, but I'll just say that out loud to be completely precise. Right, so this theorem of Evenoff is really telling us that the curve graph is sort of a good and interesting object to study. It's sort of capturing so much about the geometry of this sort of group. Okay. And one of the things that Evenoff said, so Evenoff proved this, and then after that, a bunch of people went and proved similar types of statements for other objects associated to surfaces. So they proved it for sort of very interesting subgroups of the mapping class group. They proved that this same sort of statement holds. They proved it for other graphs that this sort of same statement holds. And so Evenoff said, and in fact, they proved these sort of all by reducing to the same type of statement that Evenoff gave. So they would take their object, they would look at its symmetries, and they would show that those symmetries actually would induce symmetries of the curve graph. And then they would apply Evenoff's theorem to say, actually, those symmetries of those objects are the same as the symmetries of my surface. And so after seeing all of these results, Evenoff was like, hey, I think maybe this should always be true. Okay, so this is known as Evenoff's meta conjecture. It's sort of meta because of how vague and big picture it is. And so what he says is conjecturally, if you have an object that's sort of rich enough, it has enough structure, and it's sort of naturally associated to a surface, then it should always have the same symmetry group as a surface. Okay, its symmetry group should always be isomorphic to the extended mapping class group. And so far, this is always held. There's been sort of some examples where this doesn't hold, where the object sort of isn't quite rigid enough. Okay, so it's not quite rich enough, you could say. And so the object that we studied during the Summer ICERM program is this extension that's sort of in the same flavor as what Faye mentioned, which is the Kcurve graph, where we're going to sort of be a little bit more flexible. We're going to take the same vertex set, but now for our edges, instead of insisting that they sort of have to be disjoint, we're going to say, let's still put an edge as long as they sort of have bounded intersection. Okay, so if my two vertices intersect at most k times. Okay, so I'll give an example, right? This is an infinite family, right? For each sort of natural number, you'll get a different graph. And so I'll just give an example for the case that k equals 1, right? So now we're allowing edges between curves which intersect at most once. And so this sort of is, we sort of have the same looking subgraph over here on the right, but now we get to insert this extra edge, right, between red and pink, because those are the two curves which intersect at most once. Whereas this green curve, still, this is not going to sort of, we're not going to see an edge between the pink and the green, because these are intersecting twice. Whereas we would see an edge here if we were considering, for example, the k equals 2 curve graph. Okay. So now I'm ready to go ahead and state what we proved. But first, I wanted to sort of introduce via picture all of the main players here. So I already mentioned Tarek was our faculty lead. And then, so here's Tarek. There's me eating ice cream. You can't see the ice cream, but that's ice cream over here. There's my good friend Sunny Ying Zhao, who is the other graduate student mentor. And then I mentioned Rob. Here's Rob, Roberta, and Yassine. The person I haven't mentioned yet is Shuchi Agrawal. So Shuchi was not actually part of the Summer ICERM program, but Shuchi and Tarek, the semester before the Summer ICERM program, had spent some time thinking about this problem. And so they actually had sort of laid some of the groundwork that we used during the summer. And so although I have actually never talked to Shuchi, Shuchi is one of the co-authors on this sort of paper that has come out of this project, because sort of she and Tarek's work sort of gave us what we needed to really hit the ground running during the summer. And this is something that can often happen in collaboration, where there'll sort of be some work that happens in the background, and someone might not be involved in sort of every piece of the collaboration, but maybe they contributed some really key idea or sort of laid the direction for the project in such a sort of important way that they're still going to be sort of included and credited as one of your co-authors and collaborators because of that, even if you aren't necessarily working with them sort of the whole time. Okay, and so what did we prove? So we proved sort of the analog of Evenoff's theorem, but for this Kcurve graph. So we proved that the group of symmetries of the Kcurve graph is the same as the group of symmetries of the surface. Okay. Okay, so I'm going to skip ahead one slide. I'm not going to go over the idea of the proof. I want to make sure that we sort of have time to talk about our practical tips and what came next. Okay, so I covered now, we've talked a little bit about Summer ICERM. I gave my mini math research talk, which folks can feel free to ask more questions about at the end. Okay, and so now I want to sort of focus on this next piece, right? This what came next. Okay, because sometimes I think when you think about doing math, you think of like being up at the whiteboard, solving problems, reading papers, like sort of scribbling down examples, really sort of active, working, producing your proof. But what happens after you sort of have the idea? You sort of know how the proofs go, you sketched out a lot of the arguments, you sort of feel like you sort of solved the problem. Usually that means you still have a long way to go. So I just want to point that out. Usually that means that you're sort of just at the beginning. And what comes next, right, sort of after that sort of solution is a lot more work. And a lot of that work involves sort of writing your math down in a way that clearly communicates the problem you solved, why you solved it, and how you solved it in a way that is accessible to people who haven't spent a bunch of time thinking about sort of your specific thing, right? And so what comes next is typically a lot of writing. And that's what happened for us. We sort of, at the end of the summer, we had a pretty good idea of how most of the proofs were going to go, but we had only written up some of them. And so after the end of the summer, we spent a lot of time writing. And we spent a lot of time, as you write, this often happens, you spend a lot of time fixing holes, right? Because you find that there's sort of intuition that you've been using to sort of pick together the big picture of your argument that doesn't quite hold when you're sort of writing out the details. Okay. So we spent a ton of time writing, we spent a ton of time fixing holes. And by a ton of time, I mean that this really spanned over the past couple of years. So I actually spent a chunk of this spring sort of doing some major edits to this paper. So that's like over 2 years after the end of the Summer ICERM program. Okay, and that's very typical, right? When you work, oh, did my screen just go blank? Let me reshare, sorry about that. I accidentally hit the share content, hit the close button on my iPad. Okay. So there's a lot of writing that goes into that, right? So at the end, this was our final project. You can't see it, but I just wanted to show it because I'm very proud of it. Here's all 27 pages of our paper. Here's our cute little title page with all of it on it. Okay. And this is now just like 3 weeks ago, maybe 2 weeks ago, got accepted for publication. So again, this is like over 3 years after the end of the program. So I just, again, this is just to emphasize sort of the scale, right, that some of these collaborations are going to be happening over. And also to point out that like a lot of this collaboration after the end of the summer was really more myself and Tark and Sunny, because our undergrads, like this year after, we're applying for grad school, and then we're starting graduate programs. And so didn't have as much time and energy to sort of focus on wrapping up some of these pieces, or as much sort of experience in some of the writing. So they did sort of a big chunk of writing at the beginning, and then a lot of the collaboration was focused on sort of myself and Sunny and myself and Tark. So again, this is just to point out that sometimes sort of the balance of who's doing what on a collaboration will change over time. And that's okay, as long as you're sort of always clearly communicating what's going on to your collaborators, right? So everybody knows, everybody's in the loop, knows what's going on. Okay. And then what came next? Well, lots more math happened. So one of the things I wanted to mention is that I'll just go ahead and uncover all of these at once, because I think I'm talking a little bit longer than I intended to, which is that during that summer of spending so much time together, talking about so much math, a lot of sort of collaborations have popped out of that. So for example, while I was at the Summer ICERM program, I was working on one of my own projects on sort of length spectral rigidity questions for certain flat metrics. And this is something that I talked a bit about with Tark while we were there. And Tark asked me this question about like, hey, like what is known about unmarked simple length spectral rigidity for hyperbolic metrics? And I was like, nothing, I don't know, like we had no idea. And so he asked this question and we dug around. We found like one cool paper that sort of gave a hint that the thing that we wanted to be true could possibly be true. And then we started meeting, we started chatting. We chatted during the summer, and then we sort of started having regular meetings in that fall. And we put together a paper that didn't answer our question. So we had sort of an idea of an approach to the question that we were trying to answer. And we couldn't really make progress, but we were able to sort of prove something cool along the way about these sort of certain types of covers. And so we wrote a paper. So this was myself, Tark, Algab, Sunny Zhao, who I mentioned before, and Max Elon, who at the time was an undergraduate at Brown. Okay. And so once that paper wrapped up, we were still interested in answering our bigger question. And so we kept chatting, right? And so we have a paper now that's coming out. It's again, me, Tark, and Maxie, but then we've also been joined by Nick Miller. And how did that come about? Well, Tark and I were still interested in answering this question, but we felt like we didn't have enough expertise in some of the sort of more, these sort of questions having to do with certain representations. And Nick, Tark knew a lot about this stuff. And so Tarek was like, hey, Marissa and Maxie, would you be okay if I asked Nick if he could come to a meeting and if he'd be interested in joining? And so we had a few chats. It went really well. And so Nick joined our project. Okay. And then this last project is this project that I mentioned earlier. This was sort of the project 2 during Summer ICERM. And we didn't really make a lot of progress on that during the summer. But recently, Tarek and Brandis Whitfield, who is one of the undergraduates during the Summer ICERM, we've circled back around because there's been some new papers that have come out, which have some sort of new ideas, some new possible approaches. And we think maybe we could make some traction. Okay, so as you can see, there's a common thread here that like that time together with Tarek has led to us having some really fruitful collaborations. Okay, and it all came out of that sort of really supportive, kind, and like just excited environment that we had during that summer. Okay, so I know I'm coming close on time. I think I probably have about 5-ish minutes left, maybe. Okay, so I want to end with some practical tips. Okay, about what you can sort of have in mind in order to have good mathematical collaborations yourself. Okay, so I'll have some practical tips, and then I'll have some sort of closing questions that I think are a good way to frame a beginning of a collaboration. Okay, so these ones are tips. I'll go ahead and write them down. That may seem obvious, but you would be surprised at how often this is not actually talked about at all when you're doing math with a group of mathematicians, okay? But I think that these are crucial to make sure that everybody is sort of having an environment that works for them, okay? So first of all, it's just this idea, and I mentioned this earlier as well, of sort of setting clear expectations, right? Who is doing what when? What are we trying to do? What is the goal, right? What are our expectations of ourselves? What are our expectations of each other? Okay. 2, I think it's really important to make sure that you're really being cognizant to fairly divide up the responsibilities of your project. Okay. And this doesn't mean that everybody is going to do the same amount all the time throughout the entire duration of a collaboration, especially not if a collaboration is lasting over a long period of time. But it does mean that you want to make sure that like nobody is feeling like they're either being overburdened or that they're being sort of pushed off the project, that they're not sort of being given the room to sort of have responsibilities and feel like they're contributing adequately to the project. Okay, and of course, both of these sort of tie into this third one. In fact, most of these sort of tie into this third one, which is really just to communicate, right? To communicate to your collaborators. Communicate early and often, whether this is about what your expectations are, if you're asking what other people are expecting of you, if you're going to have time that you're going to step away from the project, let your collaborators know. If you're going to have time that you're going to be really working on the project and maybe you'd like to have time to sort of touch base with a couple of your collaborators during that, tell them, right? Communicate, be upfront about sort of what's going on, what you need, which is sort of exactly this fourth one. I think this is important to state explicitly because I think we often can be hesitant to do this in sort of our, I think any relationship, but I think especially professional ones, where we aren't necessarily always sort of clear about sort of what we need to be able to work well, right? Just be upfront. What are the things that help you be an effective mathematician? What are the things that help you be an effective collaborator? Ask for what you need. And then of course, finally, and very, very importantly, right? This is probably the most important of all of them, is that it's so crucial to treat your collaborators with kindness and respect, right? There are folks who I have collaborated with in the past who I don't think I would collaborate with again, because the way that they treated me, both during the project and sort of outside of the project, it didn't make me feel like they sort of cared about me or valued me. It made me hesitant to even sort of talk to them about the math just because of the other things that were going on. And so treating your collaborators with kindness and respect, I think, is sort of top value. Like that's very important, both so that people want to do math with you again, but also so that the math you're doing can sort of flow as freely and naturally as it can. Okay. And so then here are just a list of few questions, and I'm happy to make these slides available to folks later if that'd be helpful, but just some things to ask yourself as you go. And these are all questions that were written jointly with Siddhi Krishna, who's here. Siddhi, hi. Siddhi is just starting an NSF and RIT postdoc at Columbia, very fancy. So the expectations, what expectations do we have for each other in order to maintain a healthy and collaborative space, right? What resources do we need to be successful? So these are sort of questions that we should ask of ourselves and ask together as a group. Okay, responsibility. What responsibilities do we have to ourselves and to each other within the context of this collaboration, right? How are we sort of saying that we're going to meet every week? Are we saying that we're going to like read a paper and digest it and like share it with our collaborators? What are we saying that we're going to do? And all these responsibilities that we can meet in this sort of taking into account what other demands there are on our time. Okay, and then finally, I think whenever you talk about having expectations, you talk about having responsibility in a group of people, then you also have to have this balance of, well, what happens if things don't go well, right? How do we hold each other accountable? Okay, so this is sort of, I think, the hardest of all the questions, which is how do we hold each other accountable for our treatment of others, right? And how do we proceed if something goes wrong or it just doesn't go the way we're expecting or hoping? Right? I think answering this is really crucial so that you have a plan of action if things are sort of not going the way that you were hoping them for. If you're not feeling good about the way the collaboration is going, you want to make sure that there's a way for you to address that in a way that's healthy and that is productive. Okay, and that's all.
Let's thank Marissa for a great talk. What questions do folks have?
I have a question.
Go ahead. Who's that?
This is just a little bit of a clarification, but you said the group of symmetries of the Kcurve graph is the same, and that's for any natural K?
Yeah, so we proved it for K equals 1. And then for where K is sort of sufficiently large with respect to the topology of your surface. So for, you can say sort of for any surface, K equals 1, it always holds for the K equals 1 curve graph. But then in order for our proof to run through, we actually need sort of K to be big enough relative to the topology of our surface. It's not too big of a bound, but sort of like for a genus 5 surface, maybe you have to have like K at least like 600. That's bigger than you need, but that's sort of the idea.
And is it the case that for some of these upper bounds that you know that for smaller ones it is not the same?
No. So it should hold, I think it should hold for any K for any surface. So it's really just an artifact of our proof. So our proof is sort of using that you sort of have enough space in certain subsurfaces to be able to run some of our arguments, but that's not really an essential thing in terms of like what the geometry of these graphs are, what the surface looks like. That's just sort of an artifact of our proof. Yeah. Thanks, John. This is May, by the way. She just got a haircut yesterday. So that's why her face is so pointy.